In section 2.4, we're going to be looking at limits and continuity and the relationship between them. The first thing we need to do is look at continuity. We've already had a good look at limits already, so when we talk about continuity and relate them to limits, we first need to have a good definition of continuity. So continuity basically means we have a graph that has no breaks or interruptions. Now that's definitely not a mathematical definition, it's kind of a layman's term. Another way to think about this is you don't have to lift your pencil to trace a graph. So if we have any asymptotic lines and we have to skip to trace a graph, I have a discontinuity. So let's go ahead and look at a few graphs and then let's try to determine whether they're continuous or discontinuous based on these kind of vague definitions that we have of continuity right now. Let's go ahead and look at a nice easy graph. This looks like we have continuity everywhere, meaning every single point that I'm looking at has continuity. Now if I want to look at continuity at a particular point, let's say C, I would say that this graph has continuity or is continuous at C, at the point C. So we look at continuity as a whole along the entire graph, and then we can also look at continuity at a particular point. And that's what we're going to be focusing on today, is more continuity at a particular point. Let's go ahead and look at a graph here. And first of all, we can see right away that I definitely need to lift up my pen right here at this point, and we'll call it C. So I do not have continuity at C. So I'd say that this graph is discontinuous at C. I have quite a few problems going on here at C actually. I have a hollow point, and a hollow point's not always bad, but for this particular I have a jump discontinuity that we'll be talking about in a second. Let's see if we can squeeze one more graph in here. And again, on this one I can definitely see when I trace my graph I have a problem right here at the peak. So let's call that point C as well, and I have a discontinuity here as well. But my discontinuity in this case is a different type of discontinuity as I did in this second case. So again, first of all, let's identify whether it's continuous or discontinuous, and then we'll worry about what type of discontinuity it is. Okay, let's go ahead and look at the formal definition of continuity from your book, and then we'll kind of write it out in terms that are a little bit easier to understand. First of all, when we're talking about continuity, we're talking about continuity at a point, so please be aware of this. This is a definition of point continuity. So the definition says assume the function is defined on an open interval. Okay, so up here in what we've looked at, the function is defined on an open interval. That means it's continuous over the entire interval, in this case negative to positive infinity, or it's defined negative to positive infinity as it is for all of these graphs. And this open interval contains a point C, and you can see from all the graphs above that each of these open intervals contains a point C. And we can say that the function or the graph is continuous at C if the limiting value, and that's what this is right here, the limiting value as x approaches C is equal to the functional value of f as f approaches C. It says if the limit does not exist, or if it exists but is not equal to f of C, we say that a function is discontinuous at C. So let's look up in this case. In the second case, the limit does not exist at C, so I can't have point continuity at C. In this case, the limit does exist, let's say here at 4, but the functional value doesn't exist, so I can't have continuity. So there's three things to remember here. First of all, the limit as x approaches C from my function must exist. Okay, I cannot get d and e from my function evaluated at C. The second thing, f of C is defined. That means if I plug C into my function, I get a number back. In other words, it must exist. It cannot have just a hollow point. Now up in this particular case right here, you might say, well, wait a minute, at C it has a hollow point, but it has a filled point down here, so it is defined at that point. And the third criteria that must hold true is parts 1 and 2 have to be equal. The limiting value must equal the functional value. So those are the three criteria that must hold. If these three criteria do not hold, then that means I have a discontinuity at a point. So these are the three things that you need to remember for the definition of point continuity. And you will definitely need to know this. Tests and quizzes. So let's go ahead and look at some examples. That's usually the best way to get started to try and explain these. The first type of discontinuity we're going to look at is a removable discontinuity. Now, as from the definition of the text, it says if conditions 1 and 2, and the 1 and 2 that they're referring to are the conditions up here on the right, if conditions 1 and 2 hold true, but the third does not, you have a removable discontinuity. So remember, condition 1 was the limit as x approaches that constant c has to exist. Condition 2 is that point is defined, meaning somewhere there's a filled point above that point c. And then the third condition is saying I do not meet the criteria for that third condition. The limiting value and the functional value are different, so I have a removable discontinuity. So a graph of a removable discontinuity might look something like this. So from here, criteria 1, the limiting value exists. The limit from the right equals the limit from the left, and let's say that that limit here is 4. And again, we're looking at c. The second criteria is the function is defined, and in this case the function is defined at 5 for c. However, the limiting value does not equal the functional value. Part 1 does not equal part 2, therefore the limit would not exist. So that's an example of a removable discontinuity. Now if it's removable, that must mean that we can fix it. Well, the way that we can fix it is just redefine f of c to equal 4, and then it's fixed. And so this is called a mild type of discontinuity. We call it mild because we can fix it. The next type of discontinuity that we're going to be looking at is called a jump discontinuity. Now, in terms of types of discontinuities, a jump discontinuity is considered to be a worse type of discontinuity because we cannot fix it. Now, a jump discontinuity occurs if condition 1 is not met. Now remember, condition 1 was the limit as x approaches the constant exists. So what we're getting here is the limit as x approaches that constant does not exist. Now, each of the one-sided limits exists, but they're not equal. Remember, that's how we get in a limit to exist. So let's go ahead and look at some particular graphs. For this first example, we're going to be looking at the limits as x approaches c. So I'm going to be checking this for point continuity at c. Now each one of these is going to work the same. The first thing I always check is to see if the limit as x approaches c of f of x exists. That's the criteria. Well, how do I determine if a limit exists? I take the limit as x approaches c from the right, and I take the limit as x approaches c from the left. Okay, so let's see what we have here. I'll make up some numbers. We'll call these 1 and 2 when we plug in c. So as I approach from the right, I can see that my limiting value as I get closer and closer to c from the right is equal to 1. As I approach from the left, my limiting value is getting closer and closer and closer to 2. It actually equals 2, but remember, it doesn't have to have that equality. These are not equal, therefore the limit as x approaches c of f of x does not exist. And because it does not exist, I don't have to go any further. I know that I cannot have point continuity there. So this is discontinuous. At x equals c, and it's discontinuous because it has a jump discontinuity. And you can see by tracing the graph you'd have to jump from 1 to 2 to make this, to draw this graph, so that's why it's called a jump discontinuity. However, this graph does have some continuity. This graph does have right continuity. I'm sorry, it's not right continuity, it's left continuity. And if you want to think about the definition of right and left continuity, it kind of makes sense. The functional value at C is defined, that's I have the filled point, and the limit from the left is equal to that functional value. So that's why it's called left continuous, or I have left continuity here. Let's go ahead and look at another graph. And this graph is going to have quite a few different problems, similar to the graph we just had above. But notice here at C, I have two hollow points and a filled point. So this is still a function. It passes the vertical line test. Okay, but it does have some problems in terms of continuity. I would definitely have to lift up my pen here to determine whether I have continuity or not. So the question is, do I have continuity at C? So is there point continuity? At x equals c? That's the question. Well, remember, there's a list of things I need to check. The first criteria I need to check is the limit as x approaches c of f of x must exist. Well, in order to determine whether a limit exists or not, I need to check it from the left and from the right. So I have to take the limit as x approaches c from the right, and I have to take the limit as x approaches c from the left. Now as we approach c from the right, my limiting value is 1. As we approach c from the left, my limiting value is 2. Well, these are not equal. 1 does not equal 2. Therefore, the limit as x approaches c of f of x does not exist. So I'm done. I don't need to check anything else. I'd have to say, therefore, I have a discontinuity at x equals c for this graph. And in fact, it's a jump discontinuity if we want to be more specific. Now here's another question. Is this graph right or left continuous? And the answer is it's neither. If you notice, for each of these, my limit is 1, my limit is 2 from the left, but my functional value, which would be number 2 for the criteria, does not equal either one of the limits. So for this particular graph, I have neither right continuity nor left continuity. Now if either one of those hollow points had been filled, then I could have had either right or left continuous depending on which one was filled. And of course, if you fill one of these hollow points, you'd have to get rid of this one up here. So those are examples of left and right continuity and the different types of discontinuities.